Hi, my name is Patrick Thomson. I work at GitHub on the semantic code team. Our goal as a team is to help developers understand, write, improve, and maintain their source code. And as part of that mission, we write tools to consume and analyze the corpus of code on GitHub. And that's something that's very much easier said than done because GitHub hosts billions upon billions of lines of code. And building tools that are capable of handling that volume of data, that's not easy. I'm here to talk about a library originally written by my friend and teammate Rob Ricks that we use to build these tools. It's called Fused Effects, and it's written in the functional programming language Haskell. Quick poll here, how many of you know Haskell, even like a little bit? Well, so many, I'm among my people. How many use Haskell or have used Haskell for work, for jobs? Fewer, but some? Yeah, I'm with it. This library is called Fused Effects, and from an application level view, Fused Effects is a library atop which you build programs. It provides the basic building blocks that, when composed together, provide you, the programmer, a sufficiently expressive vocabulary to fit your need. But we can take a different view, perhaps a more formal and precise perspective, and so speaking technically, it's an effect system, one that provides higher order scoped effects and handlers for those effects that display fusion properties. If this seems like jargon, it's because it is. We'll cover in some detail exactly what that means later. And from a systems view, the nuts and bolts perspective, it's a real-world production quality library designed for applications that don't want to sacrifice performance for expressivity. Semantic Code team has built several applications with Fused Effects powering real-world GitHub features. In our experience, they've performed really admirably. I'm here to talk about how we traditionally build Haskell programs and why we on the Semantic Code team found that tradition limiting. I'll show some examples of how Fused Effects can overcome those limitations, and I'll talk about the values and trade-offs that have guided its evolution, as well as the aspects of its design that make it suitable for real-world Haskell development. But first, let's take a step back. Fundamentally, Fused Effects is an answer to a question, and it's this question: how do we build programs in Haskell? When I sit down to write a Haskell program, having identified the behavior I need to implement, how do I express that behavior in code? That is, how do I translate my intent to operations capable of being understood by my fellow humans and by a computing device? And if that question seems abstract and wide-ranging, it's good because it definitely is. The first step in getting a handle on the scope of a question like this is to define a couple of terms. I want to be precise in my speech, so let's start at the basics. My boy Lee Wittgenstein described the world as all that is the case. I hope that's not too controversial. And Edgar Dijkstra, or 50 or so years later, had a nice formal definition of computers, or at least formal enough for our purposes, as describing them as mechanical equipment that can change the world. We run computations to cause these changes, and in doing so, these computations may have access to their environment. The environment here represents not just the state of the world as it is, but the set of all possible worlds that have occurred in the past. So not just the now, but also everything leading up to the now. When we tell a computer to do something, and in doing so it depends upon or changes that environment, we call that an effect or a side effect. The adjectival form here is effectful. Interesting programs produce effects. A program that doesn't produce any effects is either a no-op or it's a theorem prover, I guess. In all other cases, we write a program and run a program so that it produces a change in the world around us. These are all examples of effects. And input and output is really the archetypal one. Printing a value to the console or to the screen or somewhere changes the operating system's environment. Your OS makes a system call and it fills up a buffer somewhere and it discharges that to your rendering device, and poof, you've got a change in the world around you. And another effect is the presence of mutable variables. We can destructively assign to a mutable variable and affect all subsequent computations that query it. That's a good and useful property of a system to have. Mutable variables are very important for so many tasks, but it means that if my code relies on mutable variables, it relies on the current environment and all environments that have preceded it that involve such assignments to mutable variables. Every common programming language provides you, the programmer, with at least some of these effects that I listed up there. And usually these effects are pervasive or universal. If I'm writing some code in Python, for example, any line of code can throw an exception or make a network call or terminate the program early. So the ability to invoke these effects is woven into the fabric of Python itself. The thing that makes Haskell different from most other programming languages is that it uses types to track effects. Haskell boasts a feature called a type system, which is a language that runs before my code runs and that checks my code to ensure to some degree that the computations I've described are semantically valid. And the fact that Haskell makes its effects explicit means that before we write line 1 of a Haskell code base, we have to sit down and think. And we confront this immediately. If you don't read Haskell, this is a type signature of a computation named the main. It specifies that main is an I/O effect that returns no result. That's those little double parentheses right there. And every Haskell program starts here. When I execute a program written in Haskell, the GHC runtime system finds a function called main and runs it. And by marking main as being an input and output effect, we're saying that running a Haskell program changes something about the world. If we didn't need to cause that effect, we wouldn't be running the program in the first place. I like this because it's expressing, using the type system, of what Dijkstra pointed out, which is that we run programs for their effects on the computer and by extension on the world at large. We can compose functions that return I/O effects, and we can build simple programs out of them. And philosophically, we can view functions that use this I/O effect when expressed in Haskell as a mini language for interacting with the computer's input and output capabilities. And many of you know what these languages are called. They're called domain-specific, since they concentrate on expressing a single problem domain. DSLs are an answer, or at least a partial answer, to the question I posed at the beginning of this talk. In Haskell, we build programs by identifying the domain-specific languages we need and writing code in those languages. Indeed, I'd go so far as to call Haskell a DSL-oriented programming language. DSLs aren't everyone's cup of tea all the time, but I like them because they make what I think is a pretty radical statement, which is that people are more important than computers. If I have to solve a problem without being able to express myself in a way that's natural, in a way that fits the language of my problem domain, I'm saying that a computer's needs are more important than my own. And I don't like that. I place human needs above the needs of computers. And that leads us to another question. If there doesn't already exist a DSL sufficient to express my code in the language of its problem domain, what am I to do? How do I build a DSL or compose existing ones to get something I can work with? Well, we do that with data structures. Despite Haskell being a functional programming language, it's really big on data structures, and most notably data structures that conform to a certain interface. And that's the dreaded M word, monads. I got 7 whole minutes into this presentation without mentioning monads. I think that's a world record. The details of what a monad is and the laws they abide by and yada, 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 that's not important to the task at hand, I promise. What's important to understand about monads is that they're a unified interface for a great many effects. Library authors provide data structures that conform to the monad interface, and we use this interface with a familiar syntax. I showed you this code already. Monads allow us, monads allow us, using the do notation and the bind arrow operation, to write imperative code in a functional setting. But the syntax generalizes beyond just I/O. Here's some code that computes Pythagorean triples with side length less than 10. And in this context, that left arrow there means choose an element in the length in the list of 0 through 10. And we can generalize it even further to something like the Zelda library, which uses the query monad to express database operations that are translated into SQL. So the upshot of this is that Haskell libraries provide data structures that are monads, and we use these monads to express effects rather than them being woven into the fabric of a language. The natural next question is, great. If monads represent effects and we build DSLs by composing effects, we clearly need to compose monads. And how do we do that? And the answer is you don't, or at least not generally. Certain monads compose trivially, but there exists no general method to just pluck 2 arbitrary monads from the ether and combine them in such a way that they always type check and their invariants are always respected. And from pretty much the get-go, this was recognized as a really pressing problem in the Haskell community, because if monads resist composition, then it makes it hard for us to express our programs compositionally, and if that's hard, then kind of what's the point of writing in Haskell anyway? So Lang, Hudak, and Jones took a swing at this particular issue, and the method they came up with, monad transformers, stuck. Each monad transformer is a data type that surrounds and transforms another monad inside. I like to think of it as sort of a jawbreaker or whatever large hard candy you may have grown up with, and that there's an element at the center. Here it's I/O, and we're building in this example a simple monad that's capable of responding to an HTTP request in some sort of web framework. So we start with I/O at the center because we'll probably need to call out to the operating systems at some point. We add the writer monad on top of it, which gives us logging capabilities. We add the reader monad on top of it, which gives us access to the immutable current HTTP request. And then we add the error monad, which lets us terminate early with some 404 or 500 or whatever the one for I'm a teapot is. And it seems like at this point we've reached the end of the line of questioning that I posed. We construct programs by writing DSLs, we write DSLs by composing effects, and we compose effects by composing monad transformers. And this is indeed a strategy that works. It's become the de facto approach for building composable and reusable code in Haskell. The two libraries that provide this functionality are MTL and transformers. Transformers provides the concrete implementation of these data types, these monad transformers, and MTL provides an abstract interface to these capabilities so that you can write abstractly rather than pinning your code to the definition of some such monad transformer stack. I'm going to refer to both of these under the umbrella name MTL, since MTL plus transformers is a little bit of a mouthful. MTL and transformers together form a library providing the tools to express and compose effects. And we call this an effect system. An effect system provides us with compositional data structures powerful enough to express interesting effects and a set of interfaces that it lets us abstract away their underlying details. And this provides us a platform for building Haskell apps, both small and large. And as it happens, I work on a large Haskell app, along with these lovely people, and one of them in the back. What's up, Doug? This year, the semantic code team, we open sourced our library for program analysis. It's called Semantic, and you can go check it out. It powers really cool features at GitHub. Semantic lets you parse, analyze, compare, and diff and interpret source code across many different languages. We currently support Python, Ruby, TypeScript, PHP, JavaScript, and Go, and I'm probably forgetting one because there are a lot of languages, with a consistent interface to all of these languages. And as much as I'd like to spend the next half hour or so talking about Semantic, this is not a talk about Semantic, but that will happen one day, I promise. Stay tuned. At its heart, though, Semantic is an implementation of ideas from a really wonderful paper out of UMD called Abstracting Definitional Interpreters. This paper outlines a really beautiful methodology for building interpreters for programming languages. These interpreters can be concrete, in that they execute the programs they're fed directly, like the interpreters for JavaScript and Ruby and Python that we all know, where you stick in a program and you get a result. Or they can be abstract. An abstract interpreter computes properties of a program without actually executing it. And this is really useful for program analysis at a company like GitHub, because we want to be able to analyze your code without running it. And what's great about abstracting definitional interpreters is that it provides a recipe to start with a simple concrete interpreter, and then, by changing the effects this interpreter can access, making it more powerful until it becomes an abstract interpreter. And here's a visual representation of the first few interpreters that ADI defines. Start with the simplest one, which has access to an environment and a heap. We add some logging, and we get one with tracing. When we add some, and then when we add some nondeterminism, we get an abstract interpreter. And when we add a state that allows us to cache previous results, we get an abstract interpreter with caching. And if we have an abstract interpreter with caching, then we're like 3/4 of the way to an analysis like a type checker, or a dependency graph analyzer, or a scope checker for your favorite programming languages. But this paper in particular poses a problem when we try to express it in Haskell. Implementing the algorithm that ADI describes with the techniques that MTL gives you is hard. It's possible, yes, but it requires that you bend over backwards to express yourself. And you could argue that this is just an implementation detail, but I think there's a little bit more to than that. I think it's a collision of values. ADI is about compositionality. The essence of the paper is about building interpreters and augmenting their capabilities by changing the monads and the effects that power them. And so as such, it places a really high value on expressiveness and compositionality. And though the MTL authors valued those things very much, MTL values other things as well, and things that are at odds with the code style that ADI encourages. Brian Cantrell, who's a great dude, a great presenter, former CDO of Joyent, has a wonderful presentation at Node Summit in 2017 called Platform as a Reflection of Values. I really recommend seeking it out and watching it, because it provides me a metric, not a perfect metric, but a metric for something that I didn't have before, that I didn't necessarily consider. If you find yourself at a technical crossroads, deciding between libraries or operating systems or some such platform for thought, and you enumerate the things that you value in whatever situation you find yourself, and you enumerate the things that your platform values, you compare these enumerations, you have a framework for understanding how well this platform will work for your given situation. How many values do you share? The more values you share, the likelier it is that you're going to have a good time, both writing and deploying and maintaining all of this. So here's a list of values that the FusedFX team keeps in mind. Some of these are generalizable to any software library. Some of them are specific to Haskell libraries, like the type inference that you have there. And some of these, most importantly, are at odds with each other. We know that sometimes the most elegant solution is not the most performant solution and not the most debuggable solution. So the development of a library, and indeed the development of any engineering process, is identifying the values to which you need to cleave and identifying the values that you may have to give up in exchange. The authors of MTL placed a really high value on performance. Code written with the abstractions that MTL and transformers provide usually runs comparably quickly to that written without any such abstractions. And it's also pretty approachable overall. I mean, monad transformers are not a huge leap beyond regular monads, and I think part of the journey of learning Haskell is expressing these transformers yourself. And MTL also values type inference greatly. GHC can look at an MTL application and figure out pretty much exactly what type each part should have without us, as programmers, having to annotate it every step of the way. And there's some things that they compromised on. Concision is one of them, and the MTL code can be very concise in the simple case, but more advanced uses of MTL require what can be a tremendous amount of boilerplate code due to what's called the n squared instances problem. And it also made compromises of expressiveness in the name of type inference. When MTL first emerged, GHC didn't have the subtle tools that we have now, like the type applications extension, that it has today to give the compiler hints as to what type such and such an expression should have. And as such, it made choices that make it easy for a simpler compiler to infer the type of a program. But these choices ultimately limit our expressive capabilities. And here's an example of this. We can see it in one such interface. This interface, monad reader, allows us to read an immutable context from a context. So that means that the ask method in some monad m, implementing monad reader, for a type CDX, returns that CDX value wrapped up in an m. If we bring this back to our example of an HTTP server, we'd say that the HTTP monad would declare an instance for monad reader such that it returned a value of type HTTP request. And that means that ask has a fixed meaning inside this HTTP monad. This arrow here, that little right arrow, is what establishes that property, that fixed meaning property. It's called the functional dependency, and what it states here is that each m, if it implements this interface, maps to a unique type CDX. So a monad doesn't have to implement the monad reader interface at all, but if it does so, then it can only do so once. We can't ask for different types of things, and that would preclude code like this. This is perfectly valid code. Like, I want to ask for the server configuration as well as the current HTTP request, but this would refuse to compile. Now, often we can work around this by, hey, we have two components, just bundle them together in some sort of data type and it will work out, I promise. But that's not always the case. Let's take a look at some of the interpreters that I showed you earlier. Each of these three interpreters their components are unique. Specifically, we don't have more than one state component in each of these. But this one is a little different. We have two state types here. One represents the liveness for a dead code analysis, and one represents the heap. And this means we couldn't use the monad reader interface to access each of these individually. We'd have to aggregate them into some top-level container type. And that's fine, but we'd have to jump through a few hoops to do that, and we'd lose separation of concerns by bundling up these two data types that don't necessarily relate to each other directly. And this one, it's even more pernicious. It's made much trickier by the ordering of effects. Note the presence of the nondeterminism effect, and because the cache lies below it, the effects of every non-deterministic computation will be made visible in that cache. However, because the heap lies above it, only the branches that succeed will make their effects visible in the heap. And this means that we can't bundle this cache and this heap together in the same data type because their access patterns are interpreted differently based on their position in the stack of the effects. Tying them together would restrict them to a single interpretation, and that would preclude this composition from working correctly. Now, it's possible to work around this with MTL, but it takes a lot of code, and it's frustrating, it sucks. And so on the semantic team, we turned our eyes from transformers and MTL, and we turned our eyes to the world of algebraic effects. We'll cover exactly what an algebraic effect system is later on, but the important thing to know for now is that algebraic effects represent effects as data types directly. As we run code written with algebraic effects, our code makes requests to what are called handlers, and they send these data types to a handler. This handler will be listening for a data type to come down the pipe. It will compute and interpret that data type in whatever manner is pleasing in the current context, and then it will provide results back to the caller. So whereas MTL is modeled around fixed interpretations, algebraic effect systems are more dynamic. A single effect can be interpreted by many different handlers depending on what context you're in. And if this is sounding like design patterns from object orientation, like observers and dependency injection and yada, 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 yeah, you're on the right track. This is not a new idea by any stretch of the imagination. It started in 2001 with Plotkin and Powers papers, where they formally proved that algebraic effect representation is equivalent in power to a monad. And so the alts saw a good bit of work on the theoretical backing, but then in 2013, the rubber really kind of hit the road when Oleg Kiselyov started using them in Haskell. So Semantic, to my knowledge, is the largest open source Haskell code base using algebraic effects, maybe the largest code base period using algebraic effects. Production traffic on github.com flows through Semantic. It specifically powers the jump to definition and find all references feature that are currently in beta, and that hopefully you've gotten a chance, if you use GitHub, to use and play with. And it's been a really good fit for us. We adopted it kind of from day one. In 2016, we forked and started working on our own algebraic effect system, which was based off the work of Alil Dev, who based her work off of Oleg's original paper. Big shout out to both of them. And it worked. We were able to work around the problems inherent to the MTL interface, and our core implementation of the abstracting definitional interpreters paper was elegant and type-safe. And the request-response pattern gave us a ton of flexibility that we gleefully took advantage of, and we were having a good time until a few years later a problem emerged and we couldn't really sweep it under the rug any longer. Historically, code expressed with monad transformers is faster than that expressed with an algebraic effect system. GHC loves monad transformers. It's able to compile them down to extremely efficient code thanks to their fixed interpretation. Algebraic effects don't have a fixed interpretation, and the optimizer pays the cost for that. So you can easily write a benchmark with Oleg's original effect library that shows it to be 3 orders of magnitude slower than equivalent of MTL code. Now, benchmarks are benchmarks, which is to say lies. Most interesting programs touch the network in some way, or they read from files or do other such high latency behaviors. And in those cases, that latency, not what effect system you're using under the hood, is going to dominate the execution time of your program. But semantic is different. The bulk of a given invocation of semantic involves interpretation of syntax trees. There's no I/O there. That's bottlenecked entirely by how performant the monads and the abstractions we're using to analyze these trees are. And these trees are big. It's not uncommon to find program texts that, when parsed, yield millions of syntax nodes and sometimes take up multiple gigabytes of memory just in their AST form alone. And when your trees are that big and the speed of your tree operations are bounded by your monadic abstraction's efficiency, and you're running this code on every single push to GitHub, you're kind of in trouble. And so here we see, again, another collision of values. We valued speed, and the Oleg-derived effect implementations didn't. It seemed like we'd have to accept the limitations that MTL imposes on expressivity in the name of decent performance. And again, this wouldn't have been insurmountable, but it would have been a huge bummer. I hate giving up the ability to express myself in the language of my domain. And it seemed like all hope was lost, but it was not. My dear friend and coworker Rob did not. Here we are at ICFP this year. I like this photo a lot. We look so happy. Rob realized that there was a solution to this problem in the literature, and the only reason we weren't using this solution was that nobody had sat down and implemented it. The papers he consulted, here they are, were written by the dynamic duo of Tom Shrivers and Nicholas Wu, whose output is just staggering. It's so good. They're on another level. They describe over these series of papers a recipe for an effect system that could compete with MTL. And it took just 3 weeks before Rob emerged with the first version of fused effects. And since then, it's blossomed into something that I think is pretty special. It's a full-featured effect system providing most of the effects you need to compose in day-to-day Haskell work, and it runs with speed comparable to MTL. We preserve the good parts of the MTL ecosystem, particularly its naming choices. So if you are comfortable with writing MTL applications, you can come to fused effects without being overly bewildered. While removing those historical limitations and sanding off some of the backwards compatibility-induced rough edges. And it's open source, it's a permissive 3-clause BSD license, it's up on GitHub, it's up on Hackage, you can go and start using it now, I do. And so the question that I'd like to get to in my time remaining is how? How did we, and by we I mean Rob and Nick and Tom, pull this off? And to understand why this is, we have to take another step back. We can go and look at this term again, see the algebraic that Finn and Jake are just so happy about. I said that effects are represented with data types, and that's the same algebraic as in one of Haskell's core features, algebraic data types. We use these types to represent effects, and here's the type we use to represent the state monad. For some state type val, there are 2 operations, one get and one put. I've color-coded both the arguments in the surface syntax and in the underlying data representation to show you that the shape of these data structures is determined by the shape of the surface syntax that we want to use. And in the real world, we write this with with somewhat fewer extra parentheses. So this is the actual data the data type that we use inside fused effects to represent the state monad. The notion of effects as data types gives rise to a really pleasing formalism of a DSL. Some program text written in a DSL is a tree. Its branches represent scoping and control flow, and its leaves represent individual effects. So if we represent effects as data type, then a tree that holds effects is code. And this gives us a nice definition for interpretation as well. If a DSL is a tree of effects, then an interpreter for that DSL is a function that rewrites that tree into something simpler, a computation that can be kicked off directly by GHC. I like these little emoji here with an ornamented Christmas tree to the regular tree because it draws a good analogy. The process of interpreting DSLs is to kind of pluck the fancy, spangly surface syntax from it until we have something earthier, more regular that we can just feed into GHC and get an answer out. You can see this visually. Here's a computation that depends on three effects: immutable context value via reader, logging via writer, and error handling via error. We got a fourth one here that takes care of pure operations. The process of interpreting this DSL is that of letting a handler walk through a tree. At each stage of the tree, a handler looks the datum held there. If it's an effect that it recognizes, it translates that into a lower level representation. As we walk the tree with handlers, we get something simpler and simpler, until finally, we've got something that depends on no effectful operations at all, at which point our pure handler can walk through and just execute the whole block of code. And this is a nice fit for Haskell as a language, because Haskell makes it very easy to represent the traversal of tree-like structures. If you're into folds or recursion schemes, Haskell is nearly an ideal language for doing operations on trees in that manner. The problem is that historically, this has been an inefficient process. In contrast to the monad transformer approach, where our semantics are specified ahead of time and translated directly to a data structure using the interfaces, this algebraic effects approach relies on repeated tree traversal. And this increases in cost both with the number of monads, both in cost with the number of effects we're using and handlers we have to use, and with the size of the trees. And this is made even more problematic by the fact that historically, free monads have provided the tree structure used by effects libraries. I don't have nearly enough time to get into the details of the free monad, but the 10,000-foot view is that they're the simplest monad capable of embedding computations, binding them, and introducing further branching and divergent control flow. And because the free monad captures these capabilities and nothing more, and that these capabilities are needed for every effect, Oleg's breakthrough was that we can use free monads plus effect types to represent code and represent DSLs. But historically, the problem with algebraic effects efficiency stem not just from the fact that we have to walk the tree multiple times, but also because the tree structure that free monads provide is not very fast to do, just really about anything. Building, inspecting, and folding them requires a lot of indirections, and those indirections make it hard for GHC to generate efficient inline code. So a lot of the immediate research on extensible effects concentrated on making free monads faster in terms of traversal and construction. There was already some research on this back in 2002. Oleg took another swing at it with what's called the freer monad, which is like the free monad but cheaper. Kamar et al. Used template Haskell to generate faster calls, and Andy McGuire's polysemi library goes even further. But there's two ways to speed up a tree traversal. You can make the tree cheaper to traverse, or you can cut down on the number of traversals required. The core idea of the paper Fusion for Free is that we don't have to walk the tree a linear amount of times. There's a long-standing tradition of research, indeed, into how to optimize repeated tree traversals. If somehow each handler was able to coalesce into a single unit, we'd only have to walk this tree once. And that would be pretty ideal. The name of the game here is to turn a linear process into a constant time process. If our handlers fuse into a single handler, we can avoid the expense of building up trees in intermediate stages. It's not always straightforward to actually make these handlers fuse in a way that GHC understands. The details are a little too fiddly to go into now. They're outlined at length in Fusion for Free. For our purposes, it suffices to state that there exists a way to tell GHC, hey, these functions absolutely have to fuse into one item. And to understand why this works, we have to consider how data structures are modified in Haskell. Because we're working in a language without mutable data structures, we don't modify a tree destructively as we iterate it. Instead, each traversal is two logical parts. It's the part that consumes an existing tree and the part that generates a new one. We call the first part a fold, and we call the second part a build. With Fusion, a pipeline of folds, then builds, then folds, then builds, then fold can be turned into a single traversal. Rather than folding with a single handler at a time, we compose these handlers and fold only once, allowing us to skip the expense of building a tree just to have it folded again. And the performance of real-world Haskell code very often depends on fusion of data structures. And our case was no exception. After switching from our effect library without fusion to one that displayed this property, I observed a factor of 250 speedups. And needless to say, that's pretty extraordinary, maybe the most extraordinary speedup I've seen in my career. And even more extraordinary than that were the speedups that have an undefined speedup because they never even finished in the first place, and then they started terminating in a couple of seconds. It was kind of scary, actually. I'd like to lay out what the values I think the fused effects team holds, at least my take on them. I think expressiveness is the big one. Fused effects exists because MTL really prevented us from expressing us naturally in the language of our domain. We want fused effects to be able to express your problem domain as well, whatever it might be, in a holistic and natural way. And performance as well. We share that with MTL. In industry, you can take performance hits of 2 and 5 and 10%, not 100,000%. We treat performance problems as the bugs they are. And we also really value rigor. Fused effects is based, as I mentioned, on a long pedigree of research, and we're confident in its foundations, and we achieve its performance in a rigorous way. There's no template Haskell, there's no rewrite rules, there's no compiler plugins, just a reliance on a long established property of GHC as a system. And there are things we downplay or don't value as much. Other effect systems are more concise. Libraries like Free or Simple or Polysemi place a really high value on avoiding all boilerplate code. And while that's a noble goal, and we don't like boilerplate either, if boilerplate and performance are at odds, in our case, performance is going to win every time. We've also not done a huge amount with custom error messages. Other libraries provide more descriptive diagnostics, and we'd like to do that as well, but we just haven't gotten around to it. And we also come with really nice things, a lot of powerful effects out of the box. I showed you this slide earlier, and here's the native concepts that fused effects uses for each of these effects. We also have things that a lot of effects libraries don't. Our nondeterminism effect is much more powerful than the simple nondeterminism that the list monad provides. It features prologue style operations, so during logical operations you can backtrack to find alternate ways of fulfilling your goals, and you can specify the scope of this backtracking with what are called cut and cull operations. And because semantic uses nondeterminism really heavily, this was super important to get right. And nondeterminism is somewhat underappreciated as far as other effects libraries go, but we spend a lot of time debugging this and a lot of time getting it to absolutely scream. Another really cool thing that we come with straight out of the box is resumable exceptions. Most exception systems let you abort from a computation by signaling some failure condition, and then you can handle that abort. But with our resumable exception effect, we're able to jump back into the computation from which the original exception was thrown in a type-safe way. This is not a feature that appears in a lot of programming languages. I think Common Lisp is the only one that boasts resumable exceptions. They're called conditions there. And even in then, they're considered somewhat hazardous because of Common Lisp's lack of type safety. But here we lean on newer GHC features to provide resumable exceptions in a type-safe manner. It's really cool. We're attempting to keep the core of fused effects pretty minimal, but we've already started working on a number of libraries to help. And so I won't read these out here, but the gist is we're committed to making fused effects be a library with a rich ecosystem. And there's one last cool trick that I want to discuss, which is one of the great contributions to the literature is a paper which I'll call What Binds Them Together. And the insight of this paper is that we restrict ourselves to modular effects. Then we can prove that monad transformers and algebraic effects are equally expressive. That means there exists a recipe for converting an effect to an equally powerful monad transformer and vice versa. So we've incorporated this insight into the heart of fused effects. Fused effects uses monad transformers to generate its code. So we get all of the research and effort that GHC has put in to making monad transformers scream, but with the power of an algebraic effects system. So I think it really occupies a sweet spot in the design space at the intersection of algebraic effect systems and monad transformer libraries. So at the end of the day, with handlers that fuse and get compiled down to monad transformer code at runtime, we've got a library that's approximately as fast as MTL, has compatibility with its ecosystem, but it provides new levels of expressiveness and flexibility. And so it's time for me to wrap up. So I'll go back to the question I posed originally, which is how do we build programs in Haskell? My decade-plus writing Haskell, this is the methodology that's worked best for me. I identify my effects, I represent them as data, I compose them as needed into a DSL, and then I compose handlers with fused effects to execute that DSL. Haskell is a language that gives you a lot of flexibility. There's no one way to do it, but in my decade-plus writing Haskell, this is the methodology that's worked best for me. If this talk has interested you, I please encourage you, go use it for fun, for work, to tell me or Rob or yell at us on the bug tracker about how you feel about it, and please file bugs when you find them. And that's really all I have. I don't think I have any time for questions, but I'd love to talk to you up here if you'd like to pick my brains. So thank you so much for coming out.